Here we have an incoming ray that is now parallel to our principal axis. And I've drawn in our normal line that, remember, points from the point where the ray contacts the mirror and it comes towards the center. So there's our normal line. How does the ray reflect? It reflects so that the angle between the incident ray and the normal line are equal. So where's it going to go? It's going to come in and then come down this way, some direction this way. Something like that. Very good. Now let's think about the geometry of this particular situation. We know the angle of reflection equals the angle of incidence. So we know this angle, the angle of reflection, must equal that angle, the angle of incidence. My condition in this case was that the incident ray was parallel to the principal axis. But if we cross those two lines with this diagonal line, we know that that must form equal angles here and here. Those are alternate interior angles. When we cross two parallel lines with a diagonal line, they form equal alternate interior angles from geometry. I hope you remember that from geometry. So we know that that angle must equal that angle. Well, if that angle equals this one and that one equals this one, we know that this angle must equal that angle. Well, what does that mean? That means this triangle here must be what kind of a triangle? They have two equal angles. It's an isosceles triangle, which means that this length, the length of this side of the triangle, must equal the length of that side of the triangle. Very good. So far, this is an exact result. These are exactly equal to each other. But we are now going to make an approximation. And we're going to keep this approximation for the rest of the time that we consider this situation. The rest of the time that we are looking at concave mirrors. Now that approximation is, let's imagine that this incoming ray is close to our principal axis. Anytime you hear something like that, you ought to immediately ask a question. How close? What does that mean? To say they're close, what does that mean, how close? I'll get back to that in just a second. Here we are, back in just a second, so I'll just tell you right now. To say they're close means that the distance between the two is small compared to the radius of the mirror. The radius of the mirror, again, doesn't mean the radius of how big is this thing this way. The radius of the mirror means the radius of the sphere of which that radius is, that mirror is an arc. So what I mean is this length here, that's the radius of the mirror. As long as this distance is small compared to this one, then the approximation we're going to make will hold. The smaller it is, the better the approximation. The larger this distance is, the not so good the approximation. Okay? So we'll just assume that this distance is small compared to the radius. Not really true in my diagram, and I'll come back to that. Not really true here, but we'll approximate it. What does that mean? If these two are very, very close together, if this is very close to this line, let's just kind of think about this. I'll kind of make a little thing here. So if these are very close together, what happens to this angle? It's a very, very small angle. And if that's a small angle, that's a small angle. This triangle is getting very, very small. What that means is that we're getting close to the principal axis and the mirror looks fairly much like a straight line. And actually I'll start drawing the mirrors as straight lines under this approximation, meaning that we're very close to the principal axis. Now obviously that's not going to be true in my diagram here, but we'll assume we're close to the principal axis so that we can approximate the mirror as a straight line. But what else does it tell us? It tells us then if this is very small and this is very small, then this length right here, if this is a very small triangle, this length is almost the same as that length. Let me redraw this. If this side over here is very short, so that it looks like a straight up and down line, and then if I make this triangle that looks something like that, so this triangle is actually this triangle right here, right there, but with a very, very small angle, then I think you can see this top side of the triangle is almost the same length as the bottom side of the triangle. If this side is very, very short, these two are going to be almost the same length. That's the approximation we're going to make. We're going to make the approximation that those two are the same length. In that case, what does that mean? Then this length is the same as that length. Well, if that length is the same as that one, and that one is the same as that one, this one is the same as this one. Which means, where is that point? That point is halfway in between the center and the mirror. That is a very important point, and we call that the focus of the mirror, or the focal point. The focus of the mirror, or the focal point. And I'll label it with a little F to indicate that point. And rather than writing this all out as the center, I'll typically just label that with a capital letter C. Very, very good. Let's keep this in mind. When we have a ray that comes in parallel to the principal axis, and we're going to assume that we're close to the principal axis, in other words, the distance from the ray to the principal axis is small compared to the radius of the mirror, and I'm not going to keep saying that approximation. I'm going to assume that approximation for the rest of our analysis of a concave mirror. If we have an incoming parallel ray to the principal axis, it reflects off the mirror through the focus. And it doesn't matter what ray we choose. In other words, we could have a ray that comes in at this distance from the principal axis. It would also pass through the focus. Or this distance from the principal axis. It would pass through the focus. Or down here. It would pass through the focus. Very good. It doesn't matter what ray we have, as long as the ray comes in parallel to the principal axis, it will reflect off the mirror through the focus, or what we'll call the focal point, either one. Very, very good. Now, let me go back over one more important point. Let's imagine we have a mirror. This could be a flat mirror, a curved mirror, it doesn't matter, one way or the other. If we have a ray that comes in and reflects off, obviously according to the law of reflection, let's imagine that this ray goes from some point A and ends up at some point B. So the ray goes from point A to point B, and we know then that the angle of incidence must equal the angle of reflection. What if we had a ray going the other way? What if we had a ray that came from point B along the same path, but this way, going into the mirror, rather than having the original one that was coming out? Well, if it comes in, its angle of incidence will have been the angle of reflection for the other ray. It will reflect so that its angle of reflection will be the same as the angle of incidence. In other words, it will reflect back along the same path and end up going through A. This is a very general result that I'll refer to a number of times. If a ray can go from point A to point B, it could also go from point B to point A, just reversing the path. If the angle of incidence equals the angle of reflection, going the other way around, the angle of reflection, the new angle of incidence, must equal the old angle of incidence. So, if a ray can go from point A to point B, it could also go from point B to point A. Very good. Let's take a look now at a concave mirror and see if it can actually make an image. Can the reflected rays coming from a particular object, will they come together and make an image? Let's see.